We're going to take on periodic properties today. Now I have several of the reasons behind what these properties are, and especially the exceptional ones. You might remember the ionization energy. There's an exception there with nitrogen and oxygen. I'll try to explain that and a couple other exceptions on ionization energy. That's where we're starting today. We'll start with, you can see this is similar to what we had in the book, a graph of ionization energy. And here's a definition of ionization energy. How much energy is required to remove the outermost electron in an atom? You certainly don't need to copy the graph down either if you're wondering about that. This is definitely in the book. You can find it easily online. Some definite trends. We see there are 3 rows represented on here from the periodic table. The first 2 elements make up the first row of the periodic table. Then the second row is from lithium to neon. And you can see generally what's happening in that row. And then the third row is from sodium to argon. You can see same kind of thing. Another thing I want you to notice is the points start high on the left, and as we go to the right, everything seems to be kind of going down like this. That indicates something as well. So how difficult is it to remove an electron is given by the ionization energy. Just to make this very clear, when something has a low ionization energy, that means it's easy to remove an electron from. And then, of course, if it's high, that means it requires a lot of energy, and it's difficult to remove an electron. All right, and then we don't have to do that. I don't want you to even write this down, but I want you to just notice what family's elements have the lowest ionization energies. If I just kind of circle these low values down here, and I even covered up 2 of those as I was circling points and neglecting where the symbols were. Down there is lithium, down there is sodium, down there is potassium. The alkali metals is obvious. They have the lowest ionization energy. It should make sense to you because they have 1 valence electron, 1 electron that's starting a new energy level. So to remove that one, it doesn't take much energy. What elements have the highest ionization energy values? Well, look up here, and what do you see? Even argon. Now argon, remember, the whole graph is kind of taking a downward turn, but helium and neon, the highest peaks there for every family, of course, are at the, not every family, every row are at the noble gases. That simple principle that you learned back in middle school probably, that the noble gases have a very stable electron arrangement, that carries through a lot of what we learn about in chemistry and behavior of atoms. Okay, now this is one of the questions that was number 2 on the reading quiz. Successive ionization energies. You need to know that with every ionization energy, another electron is being removed. When one electron is taken off, it takes a certain amount of energy. You can see, and this is kilojoules per mole, so it takes a pretty significant amount of energy to remove an electron. What happens is the atom, once you remove one electron, it gets all pulled together more because the nucleus in the middle now doesn't have as many electrons to worry about, so it can draw them in closer. So the second ionization energy is always going to take more energy. So you can see the 735 about doubled to 1400. The 580 about tripled to 1800. So, you know, there's always more energy required. But then, for magnesium, from the second to the third, it went up by about 5. There was a huge jump in the ionization energy from the second to the third. And for aluminum, the huge jump was from the third to the fourth. It went up by about a factor of 5. So you need to know that every time another electron is taken off, it takes more energy than the one before it. But when you get the huge jumps, you got to know what's happening there. So what we have, after the first ionization energy, now we have magnesium with a positive 1 charge. And the loss of the electron has pulled the remaining electrons in more tightly to the nucleus for magnesium. Now take another electron off, it's going to take more energy. It like doubles the amount of energy. So this is Mg plus 2. Now Mg plus 2, what's its electron arrangement like? It's just like neon. So this thing right here is enjoying the stability of the neon electron configuration. Now you want to try to take an electron off of something that has a neon electron configuration, you're going to have to work at it. So yeah, that's why we had that huge jump from the second to the third. And now the jump is even higher. And notice the magnitude of the 7,700 versus the 11,600 between those two. And the reason is because this is Al. It's going from positive 1 to positive 2, positive 3. Now it has become very stable. This is also the neon electron configuration. But this is the neon electron configuration with 13 protons holding them. This is neon's configuration with only 12 protons holding them. That's why it takes a lot more energy to remove it from aluminum, because there's another proton in there. It's got more positive nucleus that you're trying to take an electron off of. So it's not twice, it's about 1.5 times, 150% compared to that. Does that make sense? I hope. So that's just some of the things about ionization energy in general. This also, we don't have to worry about. I mean, what I've just done up there is kind of describing that. Now here's where we have to deal with our exceptions, the exceptions in the trend. In general, across a row, again, that would be this thing right here. In general, ionization energy starts low and gets higher. It starts easy on the left, and as we go to the right, it's more and more difficult to remove an electron. The atoms are getting smaller, and it's going to take more energy because the outer electrons are pulled and held more tightly to the nucleus. So to get that electron off, it's going to be difficult. However, and you see the however, there's 2 howevers that I circled. There's a however, beryllium to boron, and here's a however. We have to know why those things happen the way they do. I had this over on the whiteboard as my explanation for what happens. Why is it easier to remove an electron from oxygen compared to nitrogen when oxygen is farther to the right? The trend is, as we go across, that it's becoming more and more difficult to remove an electron. But then we get a bit of relief when we try to take an electron off of oxygen. Why? Well, the proposed theory is that in nitrogen, now keep in mind, these are elements in the second row of the periodic table. These are very small atoms, really small. Everything is real crammed together. So when you have very tight quarters, the nitrogen is filling 2p. 2p has 3 orbitals to it. They're all perpendicular to each other. So it's going to put 1 electron into each, and then it's done. In oxygen, we're going to take this electron arrangement and add 1 electron to it. Remembering how small and compact everything is, now we're going to experience, or the oxygen at least, is going to high electron repulsion. This has to do with the size of the atom. You can notice that in phosphorus and sulfur is kind of leveled off quite a bit, where it's a big change there from nitrogen to oxygen because the oxygen is so small and compact. With the sulfur, it's not as bad. It's a little bit lower, I think, on sulfur. If you look at another table, this actually kind of shows sulfur maybe even going up a little bit. That is not true. Sulfur is lower than phosphorus for the same reason, because you got that repulsion in there. So an orbital is a place where 2 electrons can be held. But since everything is so close together, those 2 electrons, even though they have opposite spins, and we didn't talk about the spin, but within an orbital that has 2 electrons, you have 1 electron that's going that way, and the other electron is going the opposite way, and they'll have an opposite magnetic field, which allows them to be in the orbital together. However, because it's all so close together, still you're going to have this repulsion. So when you want to remove an electron, the orbital in here with the 1 electron says, please take the other one. Man, I prefer this. So it's very willing to give up the electron. When I say very, that's probably not fair, because it's still, you know, kind of on that upward trend, and we just had a little bit of a dip. But that's why the dip. And I want you to keep in mind that be ready to explain this one, because the questions in the end of the chapter, you're going to have to remember that. I would even say when you start studying for the AP exam, you're going to notice that there's questions about that, and they love to ask about the exceptions. So be willing and ready to explain why that happens. The other exception here is the beryllium boron, and that's because beryllium finishes well, in the case of beryllium, it finishes 2s. Over here, same thing happens. Magnesium just finishes 3s, and then it's starting 3p with aluminum. What we think, and this is what is being addressed down here, we think that when a new energy sublevel is begun, and the arrangement of the sublevel, you know, you go from spherical to these dumbbell-shaped things, chemists don't think that that first electron in there can feel the nucleus very much. It's called the shielding effect, and what the theory is on it is